Hi and welcome back to Ceramics Part 3. So we're looking at ceramic objects, and all of these objects that I've got here on the table have ceramic in them. The one's the glass bottle over here. There's a rock that's a bit like limestone over here on my left. Some earthenware made out of clays, baked at lower temperatures. There's some igneous rock here, which has been finely polished. A very dense rock. So all of these are ceramics. And ceramics, the particular that we're interested in, are those that are involved with building or building civil structures. Now, we need to know something about the processes from which we can create ceramics or shape them or mould them, and you need to know a little bit about that, so I'm going to go through that very quickly now. The first process we'll look at is called pressing, and pressing, as it sounds, is very simple. It's basically pressing a clay into a mould. So it'll be a fairly malleable clay. It'll be pressed into a mould. Sometimes pressing can happen using powdered forms, very similar to sintering with metals. So you can use a clay powder, and if you do that, the process is called isostatic pressing. So with ceramics, isostatic pressing can take place. You don't need to know in detail about what isostatic pressing, but just to give you a little bit of a quick overview of a little heads up from the textbook over here. It involves putting some metal powder into a mould and using pressure from a gas or liquid to form that shape, and under heat and pressure the ceramic is formed. And it's not so much the thing that you need to be very aware of, but just to know that it is used for using some complex shapes. For example, this spark plug insulator would have been made through isostatic pressing, very high temperatures and pressures. Alright, the next way that we can form shapes is just simple pressing. So some bricks are created like this, especially bricks that seem to have a depression, which is called a frog. So this is a simple pressing. An example of that would be a brick that has a frog, and a frog is just a depression on top of the brick. So there's your brick over here like this. You'll notice on some bricks they seem to have a depression in there in the middle that goes like that. So the clay's been pushed into a mould, and a shape which is the male version of this female shape is pushed in here, and to be able to create an even shape and press the material all the way into the corners of the mould. So that's simple pressing. Well, the next thing you can do is hand throwing. So you might have seen that with you've got a pottery wheel, and a potter stands there and spins the wheel, and using the wet clay he's able to shape that clay as it spins. Obviously good for circular shapes, bowls and cups and so forth, or ornate vases. Hand shaping can be done if you're looking at small quantities, small runs. And all of these of course can be fired, or do need to be fired to maintain their stability. The other, so hand throwing is another process. A mechanised version of hand throwing is called jiggering. So jiggering simply looks a bit like hand throwing. It's the wet clay shape is pressed by a mould to create a rather circular shape. That mould then spins, and a forming tool passes around the shape, and almost a bit like a turning process, it shaves off the excess to form a round shape that's created. And jiggering is used often to create plates or bowls, especially in mass production circumstances where accuracy in the same shape is required. That's jiggering. Alright, next is extruding. Extruding, as it sounds, is pushing out some soft material through a shape. A shape, so if you've got a tube of toothpaste and you squeeze it, toothpaste comes out of that aperture in a round cylindrical shape. That's extruding. So parts or metals or objects, not metals, but objects like this would have been extruded. So there would have been a shape out of which the wet clay mould would have been forced, usually with a screw thread to push pressure behind it, forced out through the opening, and as it comes out in a long sort of line, it would have then been sliced using some very thin high tensile steel wire into the various different lengths. And bricks are often done that way as well. So to give you an example of what a brick would look like, I've got one here. This brick would have been extruded, so it would have been extruded in a long line like this, and there'll be mandrels or little forming shapes placed inside the mould and suspended, and the brick would have been pushed through there to allow for these holes and then sliced off at length. We'll talk a bit more about brick making very soon, but that's extrusion. So clays are often extruded to create these shapes, and particularly continuous, long, continuous shapes that are have the same cross section. They'll often be extruded. Alright, slip casting is another form. So slip casting is where you have a mould. I'll just write that down here about extruding so you remember extruding. Next one was slip casting. Now slip casting requires a enclosed mould, and into that mould through a hole is poured a slurry, and that's called there's a name for it. It's called a slip. So the slip, which is a very liquid form of clay, is poured into the mould. The mould is usually made out of plaster of Paris, and the plaster of Paris absorbs the water, and once the water dries and it starts to absorb the outer walls, the slip will be poured out, and the outer walls will dry, forming a shape which has hollow on the insides. And that shape, then the mould is split apart, and the shape can then be fired to whatever sort of vitrification level of vitrification is required. And this, as you can see, the hole inside here, this would have been formed through a slip mould. This is a bookend, and it would have been slip moulded. So the mould would have sat like that, and there would have been a plaster of Paris, and in fact you can see down here where the mould would have been separated along those split lines. It would have been pulled apart on two sides, and this then was fired to produce the shape that you see. And you see it's quite a complex shape, so slip moulding is very good for those complex shapes. It's also used when you want some larger clay shapes, but you don't want the weight, you want them to be hollow on the inside. So for example, sinks or toilets would have been made through slip moulds as well. Okay, so that's slip moulds or slip casting. Now let's go into actual manufacturing processes for certain items that you're required to know for your syllabus. And the first one I'd like to talk to you about is bricks. And bricks, here's our sample of our brick, our extruded brick. Bricks, very often the clay is collected from the ground, it's washed and purified, and then it's moulded and shaped and kneaded through using machines. And once it's ready in its form, it's ready to be used, and it begins to be dehydrated, so it needs to be able to lose all those temperatures. And you recall earlier on we spoke about the different temperature, the different levels of water removal from the clay slurry, or the clay mould shape, before it can be fired. So once the object is fired, it will not return to its clay shape, it can't be rehydrated again, and it's permanently changed its conditions. Sumerians were firing bricks 6,500 years ago, so it's not a new process. Okay, now the bricks that you see over here would have been, this was extruded, we spoke about bricks being able to be pressed as well, and they're fired at the earthenware type of temperatures. If some kind of additives can be put in to create different effects, and metal oxides are used to colour the bricks as well. And you can see there's a number of different items inside these bricks. So again, the properties of bricks: very strong in compression, weak in tension. Mortar is used in between them to be able to transfer forces from one brick to another evenly without creating stress points. Alright, now bricks have also the advantage that they can be small and yet be used to modularly to construct a large building or a large structure, and they can be made to any different shapes and sizes. Okay, glasses. Let's talk a bit about glasses. Now glasses are a bit of a slightly different item. They're defined as a fusion of inorganic materials that have been cooled to a solid without recrystallizing. So I'll say that again: it's a fusion of inorganic, so not organic materials, that have been cooled to a solid without recrystallization. You know, and typically when things are cooled to solid, like metals for example, they crystallize. Not so with glasses, and they are a ceramic. So 4,500 years ago, glass beads have been used in Mesopotamia, which is the Middle East area, and about from the 6th century, flat glass sheet was able to be made by melting glass and passing it through rollers to use in areas like windows. So people have been using glass for a long time. The properties of glass which make it useful in the construction industry are its optical properties. It can be transparent. It's strong in compression like all ceramics and weak in tension, so it's not good as a structural material. And minute surface imperfections, sometimes called Griffith surface imperfections, can raise tension, create stress raises that cause brittleness and fracture in glasses. So although in theory there should be quite strong bonds, very few electrons that are loose, and everything is stable, these small cracks, tiny little deficiencies in the material structure make it brittle. Now, the other property which glass has is that it's non-corrosive, and it's very easy to manufacture. And there's lots and lots of raw materials around to make glass, specifically silica. It has no repetitive structure. Most glasses don't have a repetitive structure. They're non-crystalline, which means they're called amorphous structures. So that's important to remember that. Amorphous, A-M-O-U. I better write that one down. So they're amorphous glasses. They have no consistent shape, amorphous. And they can be crystallized. You can create crystalline glass, but it tends to lose its optical clarity. Most glasses are constructed from our favourite silicon dioxide compound, and this is found in nature as a quartz or sometimes a cristobalite, and cristobalite is just this fancy name for beach sand. Cristobalite. Silicon dioxide is called a glass former, and it's called a glass former because it aids in the formation of glass, because when it cools after melting it doesn't form a crystalline structure. So it's called a glass former, which means that it cools without becoming crystalline. Sorry about the spelling of that. Okay, forming processes for glass. Oh, by the way, glass formers, it's possible, normally it would be up around the 1500 degrees to melt silicon dioxide, but using some metal oxides like sodium, calcium, magnesium and potassium, they will lower the temperature, melting temperature of silicon dioxide from around 1700 degrees Celsius to less than 1000 degrees Celsius using these metals, calcium, and calcium is usually added in the form of lime, because limestone is primarily calcium, magnesium and potassium, and they're called glass modifiers. So they're called modifiers, and they're often put into the glass mix when you're creating glass. Alright, glass is usually melted together, so the silicon dioxide, which is the quartz or the cristobalite, melted with modifiers and some recycled glass, which is called cullet, and it's then melted and then allowed to cool and solidify. The presence of impurities in the glass will usually be a locus point for crystalline growth. So an impurity inside the glass mixture will often be a seed point for crystals, and that creates a problem for us because it will create a weakness inside the glass and lowers the optical property of the glass, and that's not a good thing. So when that impurity is there and crystallization begins to occur, that's called devitrification. So it's a reverse of vitrification. It's devitrification, and devitrification means a crystallinity. It's crystallization happening, and that becomes a problem in the creation of glasses. Now, you can obtain glass ceramics if you want devitrification to happen. That is possible, and some examples of those, so very consistent structures. So these are more crystalline. Are Pyrex, so that's a cooking material. It's a glass material that will resist very high temperatures, has very very high thermal stability, which means it doesn't move much with heat, doesn't shrink or expand. It's often used in missile nose cones, as you'd expect. Missile nose cones, glass ceramics, and heat exchangers, because of the fact that they don't respond much when there's heat applied to them. Now, as far as the creating of sheet glass goes, sheet glass used to be rolled once the glass had been melted. It used to be put through some metal rollers and rolled out to into a flat sheet. But of course, there's always imperfections in the rollers, and the quality of glass wasn't as good. And in the 1950s, a process of rolling the sheet glass out onto a bed of molten tin was developed, and that's at around about 1550 degrees. This molten glass was rolled out onto the bed, and then the glass then flowed to a nice even surface, and it was cooled. And when it was cooled, it has to be cooled at the correct cool rate and cooling temperature, and that was in an object called a layer, which is a bit like an oven, specially designed to anneal the glass, stop stress raises from occurring, very much like the way you'd process metal using an annealing process. The same thing happens with glass. When you're creating, that's for sheet glass, when you're creating a glass container, for example, like this glass container over here, would have been a gob, or just a single big lump of glass would have been put into a mould. Compressed air is blown into that mould, forcing the glass onto the outside of the mould, creating the shape that you want. And this is then cooled to relieve stresses at the appropriate temperature. So that's to create shapes like the one that you see here. And yeah. Right. Now, glass fibre, on the other hand, which is used quite a lot as a reinforcing material, is created a little bit differently. Glass fibre can be up to 100 times stronger than a glass sheet. The main reason for that is because it has a very small surface area, and as a result there's less imperfections in the surface area, which gives it very high tensile, good tensile properties. So that's glass fibres. And how are they formed? Well, usually two most common ways to form glass fibres. The most common, or one of the most common ones, is called the continuous filament process. And that's where glass marbles, which are the raw glass material, fed into a heated hopper, and that hopper is, so the stuff is fed in, the hopper is heated up, and the material is then pushed through a base which has lots of small holes in it, and the filaments are drawn forth from that base, and then they're wound together or stored on a drum, or sometimes they're spun into a shape or webbing or a matting or a tape. So that's the continuous filament process. Another process that can be used is called the crown process. This is in forming glass fibres. Crown process is just like a big lettuce strainer. All the molten glass is pushed into the middle of a container, and the container around the outsides has lots of tiny holes, and the glass filament, as it's spun around, this container spins at high speed, the centripetal force forces the glass filament out from these tiny holes. And further, to make it even more sort of a random, the placement of these glass fibres, compressed air is blown into them as well, and this crown process is used, so it creates this intertwined kind of mat, and that's used to create your insulation bats. So sometimes you'll see rock wool, it's called rock wool, or you'll get pink bats. So this is the insulation batting is made using that crown process. Okay, and they can be pressed and trimmed and cut to shape. So some of the properties of glass fibres, so glass fibre properties. They can be annealed to relieve stresses, just like you would in metals. They can also be tempered or toughened, and particularly in sheet glass, if you have a nice long sheet of glass and you pour some cold air on the outside edges of this glass, causing it to shrink slightly, compress, so forces will come in on the outside, and on the inside you have a lot cooler, which cools more slowly. The result being that the outside is in tension, the inside, which is cooled more slowly, pushes outwards, and it's in compression, meaning that the glass itself is under stress. A little bit like reinforced concrete when you have the tendons placed inside, or I beg your pardon, it's pre-stressed concrete, where the reinforcing rod is tensed beforehand and then released once the concrete's set. Produces the same area where there's a great compressive force acting on this. And that's how you create toughened glass, and that's called so that's toughened glass using cold air on the outside of the glass sheet to cool the outsides more quickly than the insides. Alright, that's called tempering. Laminating is another way that glass is used, is able to be, its properties are changed. So there you have a sheet of glass, two sheets of glass. In between the two sheets of glass you've got a polymer which is glued to the two sheets, and this polymer is usually a vinyl, and the glasses are glued to it, and the result is that some of the elasticity and strength properties of the polymer are matched up as it's laminated to the glass panels with the glass. It also means that in windscreens, this is particularly it's used, if there's a stone chip in here or a crack that's created, it doesn't go all the way through the glass. Or if there's a large dent or smash on the glass doesn't fragment into shards and hurt somebody. It's glued together using this polymer sheet which lies in between the two sheets of glass. So that's called laminated glass. Used very commonly in large glass panels, in windows, large windows, or in windscreens. So it's large glass panels where there's a danger of breakage and people hurting themselves, or car windscreens are very common use of that. And until recently that couldn't be recycled, couldn't separate the two materials, but now that can be. It's been done. Alright, let's go back to some of the properties of crystalline ceramics. So these are ceramics that do have a regular repeating structure, three-dimensional structure. Crystalline ceramics. Some of their properties are this large they're very brittle, and the main reason for that is because there's large differences in the sizes of the atoms in ceramic compounds. So you saw, for example, silicon's very small, oxygen's quite large, and that's frequently the case, metal atoms being bigger and the silicate being smaller. So that means that it's much more difficult for the be slip planes. The other reason is because there's not much symmetry in ceramic crystals, so you'll get objects which are crystalline. For example, there's that rock that I showed you over here. Yeah, and you can see the crystalline structure over here. It's not an even repeated crystallinity, and which means that there's not many possibility for slip planes to slide. So it's not homogeneous crystallinity like in a metal structure. It's different crystals at different angles, and slip planes are greatly reduced. So you're not going to get a nice clean form of a cut that you would on a metal using a ceramic. They do have high compressive strength and low tensile strength for the reasons we just mentioned before. Large difference between atoms and non-regular crystalline phases. Okay. Well, phase is probably not the right term. I'd say non-regular crystalline shapes. Okay, mechanical properties of non-crystalline ceramics. So let's look at the mechanical properties. That's the mechanical properties of crystalline, non-crystalline, which are the amorphous ceramics. What are the mechanical properties? Well, here they go. Glasses, in the case of glasses, they don't deform along lattice planes very much, but they deform through viscous flow, because when they cool, they remain solid. They remain in liquid form, I should say, even at very low temperatures. The glasses are typical of this. And they will eventually, over time, start to creep, and you'll see that in some high windows where you'll get fatter edges down the bottom of the windows, a slight distortion in the optical qualities. It's because the glass hasn't cooled properly, or hasn't cooled at room temperature. But consequently, if you heat the glasses up again, they will regain their plasticity, so they can be reshaped and reheated and reformed and reused. Okay, so they don't deform along lattice planes, which aids that remelting process. Glass will also flow, I will mention that, at room temperature, but it's a pretty slow process. Okay, so that ends our talking about the properties of ceramics, of glasses, the manufacturing processes of ceramics, bricks, and also I guess we should note that these things have their particular uses, the properties of glasses in civil structures. Glasses in particular, with their optical clarity and their resistance to moisture and chemical attack, make excellent have excellent properties in civil structures. Okay, and what else can I tell you? Alright, that'll about do it. We'll do one more session here on cements, and then that'll be the end of ceramics. Okay, bye.